Um, Hello and welcome back, everyone. We have rogue chat escaping across my face. I'm going to kill off that chat. Sorry about that. Um, so, welcome back, everyone. We have with us now special guest Dr. Bill Hartmann, who, well, I have to say, your books were some of the books that really inspired me when I'm not going to embarrass you and say how old I was when I got them, but I went on to work at the 6 meter in the Soviet Union, and having your book that had as its cover those flags of the United States and the Soviet Union side by side, that was the future that I hope to be part of building. And I'm sad to say we aren't building that future, but you were part of imagining a future that I wanted to be part of. So this is a special episode for me. Now, Bill, can you tell people a little bit about yourself and basically where you are and what your research specialties are before we get into your artwork?
Sure. And that mention of the Russian period under what they called glasnost was really a terrific opportunity. And I agree with you that we didn't follow up very well on that opportunity to work with them. There were a lot of opportunities to have joint missions. They had the big boosters, we had miniaturized equipment, and so on. I got interested in astronomy at age 10, 12. Had a backyard telescope. My dad helped me build the telescope. Had several of them, actually got up to an 8-inch reflector that I used, made lots of drawings of planets. Really had photons from Mars actually coming into my eyes directly, when you're using your own telescope. And then went to, everyone told me if you wanted to be in astronomy, you should study physics first and then astronomy in graduate school. And that's what I did. So I had physics at Penn State and then came out here to the University of Arizona. And Gerard Kuiper of the Kuiper Belt fame, he was the major professor here, and he was my professor in those first years. And so I worked in the lunar and planetary lab there, and then a group of us who were Kuiper students formed where you're working now and where I'm working now, the Planetary Science Institute. And interests in origin of the moon, the surface evolution of planets. Did a fair amount of work in the 80s on Mauna Kea Observatory, not as big as the telescope you were talking about, but great place to be, 14,000 feet. My friend Dale Cruikshank and I, some of your listeners may know that name. He's an expert in telescopic observations of small bodies and what the compositions are. And he and I worked together a lot on some of the small bodies in the outer solar system. We made the first prediction that Halley's Comet would have a 4% reflectivity when everybody thought it was going to be a kind of a bright whitish object with dirt in it. So the common prediction of the reflectivity of that object was about 28%, I think, and it's very dark, very black. And nobody believed our prediction until Halley's Comet actually got in a little closer and the spacecraft flew by it, including a Russian spacecraft and European spacecraft, and they measured 4% reflectivity.
Dang.
So a lot of fun things I've worked on. I've been on 3 different Mars missions on the imaging team looking at photographs and the early mapping of the surface.
Now, one of the things that gets me about your career is you've been there for so many major transitions in our understanding of the solar system. You started studying science when we were still coming to terms with the consequences of the Chicxulub crater and the iridium layer around the Earth, when we're starting to figure out that the moon was not normal and had to have some weird origin. What was it like to be there while we were figuring out? And can you explain the process of, well, figuring out the impactful event that led to the creation of our moon?
Yeah, that's you touched on a number of interesting things. And actually, when I was a graduate student, one of my main thesis subjects was the craters on the moon and what could we learn from them. So there was a task I was assigned to as a graduate student. Actually, there's recently been a book, if I can get it on your screen, which is the history of the Lunar and Planetary Lab that Kuiper had started. And this guy over here is me.
Oh,
And what I
wow.
was doing, photographing a globe, which was a white globe, and we projected the best images of the moon onto that globe. And of course, then what that allowed was to walk around to the side of the globe. You know, the moon keeps the same face toward the Earth. So you can see there's something over here, there's something over there, but you don't get a very good look at it. But once we project it onto the globe, here I am walking around and photographing that from the side. And that led to the discovery of the big 1,000-kilometer Orientale multi-ring kind of bullseye-shaped basin, this beautiful impact basin on the very edge of the moon,
You
which made it,
mechanically deprojected the moon.
yeah, mechanically. I mean, this is long before computers. I always say a lot of my artist friends digitally could do, you know, what I spent about 2 years doing for Kuiper could do probably in 1 week by projecting images onto a globe, you know, digitally. But this was all mechanical. So these were big glass plates that were projected like an old slide projector onto not a flat screen, but the globe. But you know what has always intrigued me about that, and it gets to the question of how I got started doing science and kind of what my approach was. Um, Kennedy had just announced in '61 that we were going to try to go to the moon. And here I am, a fresh graduate student in '61, '62. And everybody else was studying, trying to get the highest possible resolution of small features on the moon. And here I am backing off and discovering 1,000-kilometer feature that had never been seen before. And I think in retrospect, I mean, I didn't realize it at the time, but in retrospect, that gave me a sense of, you know, back off and look at the big picture, look at everything that's possibly relevant. And that's been a kind of an interesting aspect for me. And just to give one more example then of the early days, I often think about how lucky I was because one day I'm sitting there in '69, I guess, as sitting in my office as a young assistant professor, and the phone rings, and I pick up the phone, and it's a guy who later became the head of the Jet Propulsion Lab, who is working on the Mariner 9 mission at that time. And Mariner 9 was the first mission that went into orbit around Mars. So here I am talking to him, and he says, "We got this Mariner 9 flying to Mars. Would you like to be on the imaging team to look at the photographs that we get from the surface?" Well, of course, that's completely the opposite of what happens nowadays because
Yeah.
we have hundreds of young PhDs and they announce a mission. Everybody wants to be on it. You write a proposal, you know, your chances of getting selected onto the mission are fairly small. And so those days, I get a phone call and I'm invited to be on the mission because there were only a half a dozen or so of us who had been really studying planets at that time. So it was such an interesting era to live through. I mean, when I was 14, I had the feeling that all the 14-year-olds knew perfectly well there was going to be space travel, and our parents all thought this was crazy. But we were at the right place at the right time, and when it was all getting started.
Now, what was it like when you first saw images of the far side of the moon and just how distinctly different it is from the near side? And how did this impact your and your collaborators' view of the moon?
There was you were mentioning craters, and of
Yeah.
course the far side of the moon is very heavily cratered. And I might say that the origin of these craters was still being debated in the early 60s. The other theory that had been around for 150 years was that these were all volcanic craters.
Mm-hmm.
And one of the arguments was that the moon, how could the moon have all these craters if the Earth doesn't have craters, if they're impact features? And of course, the answer we now know is that there was continental drift. You have masses of the Earth's surface being destroyed by subduction of one continental block over another, and so on. And of course, the Earth has rain and erosion, and a 1 kilometer crater on the Earth may last a few 100,000 years, depending on where it is. But on the moon, those kinds of erosion don't occur. So we realize that the moon has a record of the impact history in the solar system, which of course applied to other planets as well, which is why we see cratered surfaces on almost every planet, except Earth, and Venus doesn't have many craters. There's a satellite of Saturn, Enceladus, that has very few craters because it's ice and the ice is fracturing and new water is coming up. So whenever you see a planet that doesn't have craters, that's telling you that there's geologic activity going on there. And it's an immediate clue that you have a younger, more active surface. And that's kind of what my dissertation was about. Actually, there's a funny story there because I realized in 64, 65 that if these craters were being formed by impact, if I could study craters on the Earth and learn something about how frequently they're forming, then you'd have a rate of formation of craters, and I could use that to get an estimate of the age of features on the moon, the surfaces on the moon. Okay, well, about in the late 50s, Gerard Kuiper, our professor, had been working with Canadian geologists. He was putting out a book, and he had Beale and some other Canadian geologists writing in this book about the Canadians were just discovering craters all over, ancient craters all over Canada, because Canada is one of those areas that's called a shield area on the
Yeah.
Earth that hasn't changed very much. Central Canada is maybe 1 billion years old, 800 million years old. So it has a fair but eroded record of craters. And so I got the list of Canadian craters, figured out how many craters per billion years were forming, transferred that list to the moon, the big lava plains on the moon, where you have a crater here, here,
Yeah.
here, here, and made an estimate of how old those lava surfaces on the moon were. And I came up with 3.6 billion years, which could hardly be better to two significant figures. And that was at a time when there was a famous geologist who was really important in those days, Eugene Shoemaker, who had just concluded that the lava surfaces were about 100 million years old. And that had to do with some incorrectly calibrated military records of meteorites coming into the atmosphere and exploding. And they were seeing the pressure waves from these explosions, but the conversion of explosion to meteor
Yeah.
size was kind of crude in those days. But anyway, was able to use craters to get a correct prediction of the age of the lunar lava plains before we had any Apollo samples, which of course didn't come in until 69, 70, 71.
So
So that was the
you and
fun
folks
thing.
like Clark Chapman were the first ones to try and figure out, well, this area of the moon is older than this area of the moon based on counting the craters on different surfaces,
Yeah,
different geological features.
that's right. And that's been a kind of a theme for me for much of my career, coming back, particularly when I was on Mariner 9 and we get to Mars. And oh, there's all kinds of different surfaces on Mars with different crater densities. And the giant volcanoes that everybody knows about, Olympus Mons, for instance, 75,000 foot high mountain, those had few craters on them. And so, as this fledgling team member on Mariner 9, after I got that phone call, um, we had to go out to Pasadena to see the images coming in because, again, there wasn't the electronic digital transfer of images. I have a sidebar story of remembering that in the building we were at Jet Propulsion Lab, the computer area was upstairs, and when the pictures actually came in from radio telescopes, and there was a science room downstairs in the building. And one morning, I remember Carl Sagan coming running downstairs waving a Polaroid photograph because in those days, the way the rest of the team got their first look at the image was somebody would take a Polaroid photograph off the screen and then he would send it down to our room. So that's kind of where we were. And the discovery that he was excited about was that when the spacecraft arrived on Mars, there were 4 dark spots and everything else was featureless because it was a global dust storm, big global dust storm that
Oh,
hides all the
geez.
features on the ground. Well, what were these 4 spots? And well, they were the tops of the volcanoes that were sticking up. And what Carl was all excited about was this volcano was, sticking up through the clouds, and we could see the big caldera on the top, the volcanic crater on the top of the mountain, which pretty well established that that was a huge volcano.
That's
So
amazing.
I published as a team member, as I started to say, as a kind of fledgling team member, the first analysis then of what do we think those ages are for Mars. And I was coming up with a few 100 million years for the young volcanic features. And again, everybody thought that was pretty, people were skeptical about that because the moon's youngest features seem to be more like a few billion years old. And here I'm coming up with 1 or 200 million years old, much younger. But some years later, the Mariner 9 data were, let's say, 1972. In 1980, they began to recognize that we have meteorites from Mars, rocks from Mars that were blasted off Mars by, again, these big impact craters. And those had igneous lava like
So
rocks
explain
that were.
igneous. Igneous means lava-like?
Igneous is a rock that was molten material that's in solidifies into a rock,
Okay.
as opposed to sandstone.
Yeah.
Um, so we have these rocks that apparently were from volcanic eruptions that formed on Mars, and those dates were coming out a few 100 million years, 1 billion years. So it looks like our systems are pretty consistent. I still think that crater counting, it's funny because I helped develop crater counting, but I tend to be a lot more conservative on applying crater counting than some people are. So you will hear today people quoting numbers to 3 significant figures like 354 million years from crater counts. And I think that we don't have that calibrated to better than maybe a factor of 2. So, I'm saying, okay, that really means, say, 150 million years to 700 million years or numbers like that. Um, so the whole field has developed, of course, and it's been so many interesting discoveries in the first 40 years or so of our human exploration out into space. And I was so lucky, as I say, to be at the beginning because there was all this in a way, low-hanging fruit. Everywhere I looked, there was some exciting thing I could get interested in and start doing.
Now,
And we're very many people doing it.
now you were lucky to get inspired as a small child to have a telescope as a kid growing up. And in addition to being inspired with astronomy, which carried you into your planetary science career, you also had a grandpa who was a house painter to earn his living, but did amazing artwork in addition to that for his own personal pleasure. And that later would come back in the 80s when, well, science, we were no longer in the age of seeing everything for the first time. We're seeing things for the second or third time in the 80s, and you started giving us our first imagining humans there view for many different things. How was it that in the 80s you started adding to your scientific understanding these painted views into different solar system objects?
Well, I had always been interested in what, I guess my basic science question as a 14-year-old is what would it be like to be in
Yeah.
those places? And what is our human relationship to them? And what would things look like at a human scale? Um, there was a classic book. I wish I had it here on my table, and I think I don't. But it was called The Conquest of Space, 1949. It was one of the German rocket scientists wrote the book, but it was illustrated by an amazing man named Chesley Bonestell,
Yes.
and he was the highest paid special effects artist in Hollywood. But he had been trained as an architectural draftsman, so he was very interested. If he started out to paint something, he figured out, okay, what is the angle of the view? For
Mm-hmm.
instance, you take a telephoto lens, you're maybe only photographing 10 degrees worth of the picture, and you take a wide angle lens, it's photographing a very wide angle. So, first of all, what is that picture going to cover? And then he did a whole series of paintings of Saturn seen from different moons,
Mm-hmm.
where he figured how many degrees across would Saturn be. Uh,
And
and
you did
and
your own
very,
versions of that, which I'm going to bring up on the screen. So I currently have um, Mimas with Saturn rising in the background, Rhea with Saturn in the background, and I can't say it.
Enceladus, yes, that's right.
Enceladus with Saturn in the background. So were these paintings that you did inspired by Bonestell?
Completely inspired by him. And a nice part of the story is that many years later, I got to know him personally. He was in his 80s by that time, and he lived in Carmel, and my wife lived in San Francisco when we first were getting together, and we'd drive down from Carmel and visit Chesley. So I got to have a lot of personal interaction too, and get more of a sense of how he did things. But of course, what then I started trying to do was use the newest science to inspire a painting. And so I might have surface features that they didn't know anything about back in the 1940s when Chesley painted them. And Chesley, in the meantime, was still painting. I remember going up to his studio one day, and he had a big picture of the surface of, I think it was Europa. It was one of the Jupiter satellites. And he said, "Boy, the boys down at Jet Propulsion Lab," the way he put it, "are sending me the new pictures from the Voyager mission." And so, he was starting a painting as soon as he got one of those pictures. And then I was doing something like that, you trying to use the latest knowledge. I would go to a science meeting and hear someone give a talk and think, oh, nobody has ever tried to visualize what that effect would look like if you were there as a human being. And so I would go home and make a picture. And then I'd take a slide of the picture. This was still before digital cameras, and send it to that scientist. so that if they were giving a popular talk, they could show the audience what this might look like if you were there. And I always had this feeling like this whole activity was teetering on the top of a fence, that if it fell off the wrong way, there's going to be a big backlash that, hey, what's this amateur guy doing, just fooling around with painting when he should be working on his science. It could have a negative consequence. Or, hey, this is a neat idea. We can use those kinds of pictures to show what we think we're discovering. And I do think it kind of fell off the right way, so that now there's lots of space artists doing this kind of work, and there's also a lot of scientists using those illustrations to try to convey what they were talking about.
And it's your art that periodically pops up as what's being used. Recently, there was the case of 2014 MU69, which is this bilobate, this contact binary.
Mm-hmm.
And you had actually done 3 different illustrations of what contact binary objects might look like. What exactly was your emotional reaction when you saw this reddish world, where you're also one of the first people to have theorized that you can have these dark objects? What was your emotional reaction when you saw 2014?
Well, that's because I thought, hey, I remember I have a painting of something that looks just like that first photograph that they got. And do you have can you call up that set of
Yes.
the four
So,
pictures?
so for those of you on the internet, and to just let Bill know because he's not seeing this screen, in the upper left-hand corner is a gray number 8, basically. Then you have 2 brownish, highly cratered objects. Then there's a bright reddish with a bright neck object. And then in the lower right of what I'm showing the audience is the actual image of 2014 MU69.
Way out beyond Pluto, of course,
Yeah.
the object itself. So the story of those images is that I mentioned Dale Cruikshank. He and I were working on Mauna Kea. Another thing we did there was work on an asteroid called Hector, and the painting in the upper left was resulting from what we did with Hector. And what we could see with Hector was that you can observe what's called a light curve. And so here's an asteroid, and it's spinning around. I suppose it's spinning this way.
Mm-hmm.
It's spinning this way. Now you're looking just at one end. Now you're looking at the broad side. Now you're looking at one end. And we had cases like that where, particularly this asteroid Hector, which is a Trojan asteroid out near Jupiter, 3 times as bright when it was this way as it was when it was this way. So the question was, how can you get an object so elongated? So the first thing you think about is a cigar-shaped object or something like this pen. But there were reasons to think, and this had been suggested before we worked on it, that 2 objects fell together and made an elongated object. Well, that's great. You get that extreme difference on the end versus the side. But the problem is, you'd think, well, the best you can do is 2 to 1. You got twice as much area this way as you do that way. But how do you get up to 3 times as much area? So then I got the idea that, well, if these 2 things hit each other, what you see on the moon when there's a collision feature, it's brighter dust. The fine fragmented material is usually lighter colored, so there could be this brighter color around the middle. Okay, so that led to the painting that's in the upper left of that, the foursome. And then the one on the upper right and the lower left, those are 2 concepts after we began to realize from Dale's specialty that the spectra we were getting were reddish materials and not gray like the moon. And there's at least one of those asteroids out beyond Pluto that was discovered fairly early, Pholus, I guess it is. Yeah, I actually did a painting of that. Here's
Oh,
what it
that's
might be
cool.
like. There's the sun way off in the distance, about as bright as a street light. we realized that those reddish brown colors were there. So I did a couple of paintings of these contact binary-like features uh, with the reddish brown color. And there's another person here at our institute, Planetary Science Institute, Stuart Weidenschilling, who then did a paper back in, what was that, about 1980, I guess, that if something like that was spinning rapidly, and if the objects themselves were not a solid rock, but something broken up that could deform easily, that the lobes might become more egg-shaped. And so the painting, I think the painting in the lower left is the egg-shaped
Yeah.
version of this. Or maybe it's the upper right.
It's the
And then
lower
there's
left.
one that is two nice round things that were reddish colored with a bright between them. And lo and behold, the first painting coming back from 2014, MU 69, looked an awful lot like that painting that I did. Now we're still waiting to get the true shapes of. We had that first picture from the spacecraft, but what I'm hearing is that those objects may be more potato shaped, not nice round spheres.
Yeah.
So we'll still wait and see what the details of the shapes look like. But it's fun to interplay the scientific data with a visualization of what would it be like if you could see this with the naked eye.
And
And
that's
that's kind of big motivation.
and that's really something that you've focused on doing a lot in your work. Here I'm looking to bring up you had an image of a little lander on Mars with two astronauts climbing a hill with their hiking poles. It looks like they have GoPros stuck on the end of their hiking poles, but this was, of course, in the days before GoPros. Behind you, you have that amazing painting with a dark blue sky of Mars. You've really had a love affair with trying to make it clear to us what it would be like to be on Mars. And can you tell us, well, first of all, where that originated and what you think of all of our current efforts to see Mars in true color?
Yeah, a lot of things we could talk about. The last thing you said was Mars in true color. That's a real issue, and I think this question about the sky color on Mars. I mean, you mentioned this painting that's back here, which is 1973, and you can see up the top there's very dark blue sky because everybody, the scientists, would tell people like Chesley Bonestell, the artist, that okay, the sky on Mars is the air pressure is like at 100,000 feet, so it's going to be that very dark blue color. Nobody realized how much dust there was in the Mars atmosphere. So there's a sense of do we really understand what the Mars sky colors are? And I'm more and more convinced that it really can change from day to day and over longer periods, because when we have those global dust storms on Mars, if you're above the atmosphere, you can't see the surface. If you're down on the surface, you're not going to see the high sky. You're going to be able to see where the sun is, but the sky is pretty opaque in terms of the dust. And so I think that the sky colors on Mars may vary from day to day with just how much, or month to month, or season to season with how much dust is in the atmosphere. But it all goes back to that first story I told about discovering Orientali by backing off. This is to paint a picture of Mars or what it might be like on a satellite of Neptune. Is an effort to kind of back off and think about the big picture. What is everything we know about that subject? Because as scientists, we're taught to kind of focus on a particular phenomenon, and most scientific papers are about one person's writing about the chemistry of the rocks on the surface of Mars. Another person is writing about the photometry of the atmosphere. There's all these individual papers, but if you go back 20 years and try to understand what did people really think that those planets looked like, then if you go to the Astrophysical Journal, for example, or the Astronomical Journal, you see individual aspects, but you don't get a synthesis, and it's the artist's job to synthesize. So I think that the painting is the effort to synthesize what we know about the science. It's also an effort to be a little more experiential. And by that, I mean that, and I go out and sit in the desert and paint for maybe 3 hours to make a painting. And you just get a sense of all the things that are actually happening or not happening. In our desert, often it's sit for 3 hours and virtually nothing happens except that the sun has moved a little bit across the sky. And I think, hey, that's like Mars, except sometimes we see those dust devils going by.
And I just brought up one of the pictures of the desert that you sent me. This is summit of Red Cone Camp. And
oh yes,
and one of the amazing things about your artwork is you take the idea that the science that applies here applies there, to the point of going out and studying lava flows on the Earth, studying rock formations here on the Earth, and taking what you learn from studying terrestrial geology and incorporate that into the artwork that you do for other worlds.
Yeah, it's attempt to use what we see here experientially, viscerally, to study the data from another world and try to understand how that applies to another world. And I think an example of the opposite of that is the numerical models. You were talking about some of that a little bit earlier today. Because to do a numerical model, computer model, you're thinking an awful lot about what are the right equations, what is the best value of each parameter, each number that has to go into that equation. You're running the computer, you come down every morning, you turn on your computer, your whole world becomes that computer model. And I see that a lot, particularly in meetings in the last 5 or 10 years, that younger people are being trained to do that. But I feel like there's a lack of the experiential knowledge behind that, a lack often of backing away from the computer and saying, well, what are the other scientists getting? What are the ones getting that are looking at the chemistry? What are the ones getting that are looking at the dates of the rocks? How is sunlight shining off of these rocks? What is the color of the Mars sky? I was at a Mars conference in Iceland a few years ago, and most of the papers by younger people were models. It was a conference about the polar cap.
Uh-huh.
So all the discussion was about these models and, well, what is the chemistry and what temperature does the ice change phase? And finally, a guy from NASA about my age, one of the old guys, stands up and said, what does this have to do with the real Mars? And he kind of meant what I'm talking about. It was, yes, this is a very nice mathematical model. And when it's used correctly, of course, you can change the values of the parameters and find out which physical aspects or chemical aspects are more important, which ones are less important, and what are the most important things going on in this Martian polar cap or whatever. But you still want to think about, well, if you were in a spacesuit and magically transported to Mars, what would you look for? What would you look at? You wouldn't turn on your computer and spend all your time looking at the computer. You're out there on the surface of Mars. What do you do?
Well, nowadays, I'm afraid that some people would actually just sit there and look at their computer. That is the reality.
You said that. I didn't say it.
Hey, I'm just calling it the way it is. And I'm pulling up currently your webpage of all your amazing imagery of Mars. I especially love the fact that you painted back in 1985 a Mars sample return mission, and now, well, we're gearing up to send the first half of a sample return mission to Mars.
Yeah, the concept of that was between Russia and America again, when we
Yeah.
had that golden chance to work with them. Because there was an idea that, let's see, how did that go? That I guess the Americans would build a rover that would drive around and pick up some samples and do some simple measurements. So that would be great if it worked. But the Russians at the same time would put down a return vehicle that would land on Mars. The American rover would come over and put its samples inside the Russian vehicle. The whole thing would take off and come back to Earth. And that was, again, a beautiful concept for a mission. But again, politically, there were a lot of people, I could name some, including some former astronauts, who were just absolutely against. I remember one of the people I'm thinking of saying to me, "We can never let the Russian aerospace industry evolve again. We're going to do everything we can to prevent them from pursuing these kinds of things." And there were some of us who were younger ones at that time. We were kind of the young Turks, particularly after the Challenger explosion.
Yeah.
I was on a committee, and another friend of mine and I were talking about, well, the committee was faced with what do we do now for launch vehicles?
So this was
do
back
we
in
have?
1986, and
Yeah, yeah,
so the explosion was in
yeah,
January of 86, and there was a multi-year halt to launches.
yeah. It was maybe perhaps that summer or the next year, but there were, NASA committees and National Science Foundation or National Academy of Sciences inquiries into, what should we be doing? What's our long range program? And we were talking about, there could be a chance to build some cooperative activities with the Russians, which would be good for everybody in a way. That's the how are we ever going to get the countries working together unless we start off in things that don't threaten people. And the book that you mentioned when you were in Russia, and it was a book that a group of us artists put out that had the Russian and American flag sitting on Mars side by side, and that resulted from a really interesting set of invitations that our astronomical art group got from the Russians after about 87. They were riding high, and it was an anniversary of the first Sputnik. And so they were inviting American groups to come over. And so we had a big artist delegation of space artists and put on an exhibit in Moscow, which was then brought to the National Air and Space Museum. And there was a lot of person-to-person contact and desire to, how are we going to work together? And the more technical people and high-level politicians and creative people, artists and writers who can get together with countries that we don't like and start working together, pretty soon you have at those higher levels friendships, and people begin to say, hey, it's better for us to be doing peaceful cooperative things, and the public can enjoy this and see it happening, than to either refuse to talk or to be trying to damage the other person's economy.
Yeah, it's a complicated issue, and I think it's beyond the scope of us mere scientists trying to answer.
Yeah,
You've
they don't have the final answer, but I think we can be part of it,
Yeah,
and really try to get those working relationships happening.
it's very true. It's very true. Now, this conversation has gone faster than I could have ever imagined. We are running beyond how long I told you I was going to keep you. Um, One thing.
Fine.
I'm glad. I'm glad it's fine. Now, I have to admit, you were an inspiration to me. I am a fledgling space artist myself, and there are others out there, and there are probably others out in our audience who are currently trying to figure out how do I become a scientist? How do I become an artist? How do I get away with not getting my wrist slapped because I'm spending time doing art when I should be making a research? Um, how would you recommend that people find that balance like you did that allows them to fall on the correct side of being a scientist who also does art and being an artist who is a scientist?
I think the answer maybe is different if you want to put your principal efforts into science or your principal efforts into creative work, art or writing. Um, and under our society, I think, if you really want to spend your most of your time with the creative work, you better have a backup job. It's a basic salary job, and then hope to make it big, or get your work better known, and maybe begin to get income from the creative work. If you're in a science job, I mean, your career, if you're trying to get a science career started, that's that's a little clearer because there are certain courses you need to take in college and probably go on to graduate school. I do think there's an interface there, though. I think there's more and more interest among scientists and, say, even museum curators and so forth, to have people who can take the science and make the graphic arts out of it, so that the science program can, as we talked about, can show to the public, this is kind of what this result would look like. So there are definitely positions within science for artists. And so that would be, if you're going to be the painter or the graphic artist or the digital artist who works in that field, take take the science classes as well. Take and get the background in science so that you can know what to paint, know what goes in those images, know what goes in that novel.
And Larry Weird and Proud in our chat is bringing up a quote from Carl Sagan, who you mentioned earlier. This is a quote from his book Contact. You're an interesting species, an interesting mix. You're capable of such beautiful dreams and such horrible nightmares. And you've been part of helping to create those beautiful dreams by giving life to so many different scientific realities that, well, with your paintings, we can see them in a way that we can't necessarily see them in our data tables and our computer models. What are the things that you're looking forward to painting next? What are the things that you're working on right now?
Oh, wow. Well, thanks for all those nice comments, by the way. And I'm glad to have people looking at my website. We have some galleries of, like, a Mars gallery and a Moon gallery and a Paris, France gallery and so forth. So yeah, help yourself and take a look at those. Next, I have a novel that's a third novel. Two novels have been published. The novel sitting on a desk in New York, Daw Publishing. I've got an editor who's very empathetic and looking at it. But I've noticed with all of those novels that it's a long process to, first of all, find an editor who is interested and then get them to look at it, because they have a stack of 20 other books on their table that they're supposed to be reading as well. So that's been delayed for a while. But that novel is going to deal with, for instance, the idea of asteroid mining. Also, a very interesting technical idea of putting material. Some of your viewers will know of the Lagrangian points. The L1 point is between the Earth and the Sun. And if you put material there, it tends to stay there. You have to do a little tweaking to keep it there. But so there are actually some engineering studies of putting diffuse material, not a big metal shield, but lots of small objects at that point, and block 1 or 2% of the sunlight, and that would have a noticeable cooling effect of a degree or two, without doing any chemical alteration of the atmosphere, big environmental changes, and you can easily get rid of those things if something is going wrong. I think it's a really neat idea. And the economic studies of it, it's totally impossible to get enough of that stuff there with our technology today, because every country would be having to do practically nothing but build rockets to launch enough stuff to get there. But my novel is set in 2084 with a little nod to George Orwell, 1984, and trying to think of some positive kinds of things that would respond to the problems we have in our generation today. And so I think that once we have a capability to operate in the inner solar system pretty much at will, then a lot of those costs go down, and it really begins to be feasible to build enough stuff to get that thing at the L1 point. And that also comes back to the asteroid mining. I've written a book about the Coronado expedition in the 1500s here through Arizona and up through Mexico.
This was a Spanish explorer traveling on behalf of Spain, essentially.
Coronado, Cortez had come into Mexico City and conquered the Aztecs, and then they started hearing rumors of big cities to the north. So, that kind of exploration interests me. It's really a parallel to space exploration. And my point about asteroid mining is that most of the community today is gung-ho about what I call the 16th century model, go out and plant a flag and now it belongs to you. And there are some of the American entrepreneurial companies, there's at least one who has, publicly taken the position they want to establish that legal precedent of private property ownership of materials on a given asteroid.
Yes.
And I think there will be a lot of debate about that. And in my novel, I'm trying to encourage that debate, because I think just the 16th century model of whoever gets there first now owns that asteroid or some large part of it, that begins to be like the 16th century model. And that means that the countries that happen to have wealth in the middle 21st century will end up owning all the countries, the companies, the families. They end up owning all the resources in the inner solar system, and that will just exacerbate the problem of the gap between the wealthy have countries and the poor countries, and make the gap even worse, and all the hostilities that come with that gap. So I'm trying to deal with that in a novelistic way. That the thing I like about writing fiction or writing novels is that you can kind of deal with everything and be much more spontaneous about it. If you're writing a scientific paper, as you and I know, that's very tightly prescribed.
Yes.
What is the format? Should the references be? And the novel is kind of the extreme other end, where you're free to just throw out ideas. And so I'm hoping, I'm feeling good that maybe that will come out shortly. And the title we have on it now is Galileo Underground, because the first novel I had was Mars Underground, and this is a bit of a continuation of that universe that was in the first novel.
Well, we will definitely have you back when these books come out. This has been a tremendous experience getting to have you here, getting to hear all of these stories, and I know that there's so much more you have to say, and we could just keep going forever, but at a certain point, the science has to get done too. Thank you. This has been amazing, and thank you, audience, for sticking with us throughout this extra long edition, staying through the daily space and joining us in this learning space. This is a production of CosmoQuest. This is your place to learn and do science. And We bring you the daily space most Mondays through Fridays at 1 p.m. Eastern, 10 a.m. Pacific, 6 p.m. London time. We have the Sunday Science Hour with Annie Wilson, same time, same place. And then, of course, we are here to bring you launches, landings, and other special events as they happen. The learning space, which is taking place right now, is something that we are working to bring back, and we'll be celebrating this intersection of science and art in the weeks and months to come. What we do is because of you. We are sustained through the generous contributions of individuals, and we are so grateful for all that you have had to give. So thank you, the audience, for allowing us to be here and sticking with us and supporting all that we do. I am now going to roll the credits and then find someone to raid. So stay tuned, because while the science may be stopping here, it is going to keep going. Well, it's going to keep going across Twitch. So thank you so much, Bill, for being here. This has been an amazing treasure. Come back someday?
Oh, I'd love to. It was lots of fun. And thanks for all your kind comments.
Oh, thank you. And thank you. And wherever you are in the world, have a fabulous morning, evening, or afternoon. And remember, get outside, stop looking at your computer, and look up at the sky that we all share. Bye-bye, everyone. Okay, they can no longer hear us. Thank you so much for being here. I'm currently looking for a channel to raid, but I can do that while talking to you. So you enjoyed that? It was awesome. You really were an inspiration to me when I was a kid. Oh, I know. Yes. Yes. Oh, they still hear us, apparently. Okay. Well, that's okay. So we are now rating Oh Bother.